Hello there. It's Kim Coach Powers, and we're about ready to talk about some solutions. So I hope you are ready to learn about a topic that is really cool and yet really confusing. And for me personally, one of the most annoying topics that I get to talk about because of the strange, slightly or largely gray area definitions that we're going to be talking about here today. Okay, so anyway, here we go. Let's talk about it. We have got our objectives here today to compare and contrast the properties of suspensions, colloids, and solutions, and then to identify different ways to separate these types of mixtures. Okay, so let's dive into the first one. Heterogeneous mixtures. What is a heterogeneous mixture? A heterogeneous mixture is a mixture that you can see the difference inside of it. Okay, so it doesn't have a fixed composition. You can imagine things like fruit salad with the different types of fruit, granite with the different little specks and lines through it, dirt where you have tiny little specks of that and the other. If you can see the difference with your naked eye between different parts of the substance, different phases of the substance, not like the phase of like solid and liquid and gas, but if they're all solid and you can see like some differences there, then we're talking about a heterogeneous mixture. Okay, now one that's probably classic that you think about all the time is like oil and water, right? Oil and water don't mix. We've talked about those things. Now we're going to use a term called immiscible to describe that. IMMISICIBLE, right? So this term immiscible here is the term that we're going to use to describe liquids that don't mix with each other. Now, this sounds a lot like immixable, like you can't mix it, and that's a good way to remember it, okay? Immiscible means that you're not going to be able to mix it. Now, we talked about at the beginning, one of our objectives here is to try to figure out how to separate different types of mixtures. Well, one of the ways that you can separate different types of mixtures is right here, and it's called decanting. Now, decanting, if you can kind of think of pouring off one layer of liquid, like imagine an oil and water mixture, and you're slowly pouring off one until you get as much of that off as you can, and then the next liquid layer is about ready to start pouring out, and then you don't want to let that one pour out, so you stop. Okay, decanting is a slow process where you allow the less dense liquid to come off the top of the greater density liquid, and you're going to use that to separate those different immiscible liquids. Okay, all right, so heterogeneous mixtures, oil and water, oil and vinegar, things like that. Now this brings us to this term called suspension. Okay, and a suspension basically is defined as a mixture that is going to slowly allow some things to settle out. Right, so the more dense particles are going to settle away from the less dense particles, and so we call this a suspension. You might be able to stir it up and it might be uniformly cloudy for a while, but over time it's going to slowly settle out. Now, how can we separate these mixtures? Like a suspension, you can separate it with a filter paper, right? So imagine like a coffee filter, coffee grounds and things like that. If you just put the coffee with the grounds and stuff like that, pour it through the filter, then only the liquid comes out and the grounds are going to stay in the filter. And so using filters is a great way to separate suspensions. Remember that if you mix this thing together thoroughly, you're probably going to have so many particles in there, you're not going to be able to see light pass all the way through. Now, this is the first thing that it's going to kind of start to annoy me about these definitions, and it's something we're going to learn about here in a little bit. It's called the Tyndall effect, whether light can actually kind of scatter as it goes through a substance. Well, a suspension, after it starts to settle, it's got various size particles in it. Now, you'll notice that the particle size here, it says, is bigger than 1,000 nanometers. But remember that in a suspension, like a real world application suspension, you've got some particles that are bigger than 1,000 nanometers. Those are going to settle down. But you also have some particles that might not be that big. And so inside a suspension, you're going to have things that, for instance, we'll learn about here in a second, particles that are colloid particles, particles that are solution particles. All right, so if you have a mixture of dirt, for instance, dirt and water, some of those particles are going to be of colloid size, and they might say, actually kind of hanging out in there instead of instead of temporarily being suspended and falling out. Colloid particles actually kind of hang out inside the water. And so that's why I kind of get annoyed by some of these definitions. We might define something as a suspension, but really it's a little bit of a gray area because probably there are particles inside that substance that are having varied sizes. Anyway, that's annoying. But one example here is flour and water. If I took flour and water and mixed them together, we're giving you that as a good example of a suspension, but honestly, some of it would settle out. You could shine a light through it and you would see the Tyndall effect, which would be like, oh, that's not a suspension because suspensions do not allow light to pass through. When they're all mixed together and it's really stirred up, you might not be able to get the light through. But after it settles down, you're going to be able to see light going through sometimes. Anyway, so yeah, you have different sizes of particles. Some are going to scatter the light. And that term, Tyndall effect, is the term that we're using to describe this process where light is getting scattered, okay? And basically it means that you're going to be able to see the beam of light traveling through the liquid, if it's a liquid suspension. All right, so here are some visual examples of suspensions. And this, in this case, you can imagine over time you have this pulp type of orange juice, right? And the pulped orange juice, you can see, has like this little layer right here where it's a little bit thicker. And that's because you have all these little particles of the oranges all just kind of hanging out down there at the bottom. So this is a great example of a suspension where at one point it might actually be kind of suspended, but then over time it's going to settle down, right? It's going to fall down to the bottom. You're going to get all your little orange pieces down here, all that pulp down there. And so that's a great example of a suspension. It's also a good example, you'll notice, we use the term over here of a heterogeneous mixture, okay? So heterogeneous mixture, you can see the difference with your eyes. I can see the difference with those little particles with my eyes and that pulp material. And it's a suspension because it settles to the bottom. It forms a couple different layers. Another good example, vinegar and oil. All right, and here we have some salad dressing. The oil layer, you'll notice, is all collected up at the top here, right? So you got this big layer of oil, and they've separated, the vinegar and the oil layer have separated because of different polarities, not different densities, but different polarities. And you can see all these little particles of stuff. They've all fallen down to the bottom too. So this is a great example of a suspension that is allowing particle size to make these things fall to the bottom. The water molecule's kinetic energy, that's energy where it's just moving around, it's not great enough to hold these things up any longer. All right, so that brings us to homogeneous mixtures. Now, homogeneous mixture, you can't see the difference throughout the substance. It seems to have a uniform composition when you look at it with your naked eye, okay? If you examine it closely, you're not going to be able to see the differences. Why? Well, the mixture does have different components there, but they are too small to be seen. Now, typically, we're going to use the human eye as the measuring device. Why? Because microscopes have gotten better and better and better. And, you know, we have microscopes that can see down to the atomic level now. And so if we use a microscope as a measuring tool, then what microscope level or what microscope magnification are we using? So I like to take and use the definition of our naked eye as our measuring tool. Now, the book might actually talk about using a microscope, but I would rather you think about the human eye is what it is that you're using to measure that homogeneous mixture, whether it's a homogeneous mixture or not. Good example of homogeneous mixture is like salt water, where you can't see those little salt particles, but they're spread throughout evenly, okay? The number of ions is the same throughout that entire mixture, and that's a good homogeneous mixture. Okay, so let's look at a few different types of solutions. Now, first one we're going to look at is the liquid solution. And you might be like, well, isn't that the only kind of solution there is? No, we're going to talk about some other types of solutions as well. But if we look at the liquid solution, a lot of times it's going to be transparent. Now, this does not necessarily mean that it is clear in terms of like there's no color. You can have transparency and still have color, right? So think about Kool-Aid. You look through Kool-Aid, it's got color, but you can still kind of see through it. Over time, a liquid solution will not settle, okay? You also are not going to be able to filter it. Wait, so if you can't see it settle and if you can't filter it, then how are you going to separate, right? One of our objectives is to figure out how you separate these different things. Well, We will talk about that, but I bet you can figure it out as we get going. Separation probably has something to do with some heating and condensing. Okay. In a solution, you are not going to see that beam of light show up. The Tyndall effect is not going to show up in a pure solution. Now, and again, this is where it kind of annoys me, because if you talk about a high intensity laser beam, you can see high intensity laser beams even through sugar water. So here we are calling sugar water a homogeneous mixture, right? Why? Because it's got these really, really small particles. But can you see beams of light? Yeah, if you use the right type of light, a big, strong laser. Now, the particle size is less than a nanometer. Okay, that's kind of the definition of a solution, is that it's going to have particle sizes less than a nanometer. But you might say, well, is the sugar particle really that small? Yeah, sugar particles can actually be bigger than that. And again, so this is why, like, we call it a solution, but does it really meet the criteria? There's so many different little variations in this definition that annoys me. All right, so anyway, solution. That's a homogeneous mixture where two or more substances are uniformly dispersed. The solvent and the solute are the two components of a solution. You'll notice here, a solution is equal to the solute plus the solvent. The solvent is going to be the thing that is present in the greater molar amount. Okay, so if I had like salt water, water would be present in the greater molar amount, and so water would be the solvent. In fact, water is oftentimes called the universal solvent. The solute is a substance that dissolves in the solvent, and so if we were talking about salt water, then the salt would be the solute. Okay. All right, so let's continue on in homogeneous mixtures. Remember that the term miscible means that they are able to mix together and form a single layer or a single phase. And here's that term that I was saying would be used to describe what we do to separate these things. I said it involved heating and then recondensing, and that's distillation. Distillation is a method that we use to separate those miscible liquids. If they have different boiling points, then one starts to boil away earlier. If I just raise the temperature really slowly, one starts to boil away earlier, and then you're left with the other one down behind. Now, if I were to have a still, you guys have probably heard of stills, right? Back in the Prohibition era, people were running their own stills, and basically they would ferment their own alcohol, or make their own alcohol by a process of fermentation. They would put that material in a still, and it's going through distillation. The alcohol has a lower boiling point. Excuse me, so it's going to evaporate out first, and then you recollect that alcohol, and then you do that a few more times if you want to get it really purified. All right, remember though that liquid solutions don't necessarily contain water. For instance, petroleum has gasoline, diesel, and fuel, and that is not got any water in it, and yet it's still considered a liquid solution. We also have solid solutions, something like an alloy. Okay, so 24 karat gold has got a mixture of gold and other materials in there. And so if I take and I mix different metals together and yet they form one homogeneous mixture where I can't see the difference throughout, we call that an alloy. Two or more metals that are melted together and then cooled. Okay. And then we have gaseous solutions. For instance, air. Air is made up of nitrogen and oxygen, carbon dioxide, argon, et cetera, right? And so we have gaseous solutions as well. We also have things that are liquids that are dissolved into solids. You're like, what? Yeah, amalgam, which is what they used to use to put inside people's teeth. I still have some silver fillings in there. That's an amalgam. It's a solution of mercury, which of course we know is a liquid at room temperature, that is dissolved into the silver. Okay, and you may have seen some pretty cool little YouTube videos before about mercury and silver. Some really interesting things happen with that. All right, that brings us to colloid. Now, so we've talked about the suspensions and now the solutions we just talked about, and now we're going to talk about colloids. So three basic general categories that we're using to talk about all these different types of mixtures. Now, a colloid is interesting because it has a particle size that's in between that of our solution and our suspension, right? So somewhere in between there, which means it's a particle that's big enough to not settle, right? Water's kinetic energy is able to hold that stuff up there as it's moving around. It's able to stay and, with the attractions of the water molecules to the substance, et cetera, it's able to stay in solution without falling out. It's also not going to filter through larger filter holes, right? So maybe you have a really, really good filter. You might be able to filter out pretty much anything, right? Any sort of impurities. But you definitely do see the Tyndall effect. The colloid is what is known for the Tyndall effect. So if you see the Tyndall effect, you're thinking, that's a colloid, okay? That's kind of the way we want to get you to associate those concepts. Jello is a good example of a colloid. If you take a drop of milk and put it in water, now all of a sudden the water has beams of light that show through it because it's scattering the light and pushing it up to your eyes. Fog, when you drive through fog, that's a good example of a colloid. Here's the Tyndall effect, okay? So I want you to notice how we have this line demarking where that light is going through. And over here, you can maybe see it just a little bit. But the idea here is that this one is a colloid because you can see that light being scattered really well. This one you can't see as well. Now, part of the problem with this little demonstration that they're showing you here is that the more the further away you are with these light beams, then the less it's going to shine and show the Tyndall effect anyway. So this is a little bit misleading here, besides the fact that you can kind of see a little bit of it still, right? So it's, well, maybe that's still a colloid. All right, so let's just kind of create a little table, and I'm going to have you guys just kind of create this table. You can pause and then come back. And then we're going to fill it in just to kind of show the things that we already know. So in the top column, in the top row there, you're going to be putting down the properties or the definitions of suspensions, colloids, and solutions, and then we'll talk about how we separate them. All right, so you're back now after a little pause, and you can see we've got a suspension like orange juice that has pulp in it that we'd separate with filtration. Colloids, things like coffee with cream, gelatin, egg whites, paint, whipped cream, milk, smoke that's in air. Now, how do we separate those things? Well, there's a few different ways. One of them is maybe you could heat it, right? And so you might be able to evaporate something. Adding a salt might actually attract some particles where it would actually work to separate them. Electrostatic precipitation in a smokestack, they have the electrical grid up at the top. As the smoke goes out, it pulls all the impurities toward itself. And then we have our liquid solution. Things like coffee, right, has a little liquid. And solid at 7-Up has got liquid and gas, right? The carbon dioxide gas. What's the solid in coffee? Well, you're talking about the components that are, that make coffee up, right? So you put the liquid and then the coffee grinds together, and then all of a sudden you end up with these little tiny solid little pieces that are now dissolved into the coffee. Gasoline, two liquid things dissolving in with each other. And then how do you separate these things? Boiling water, distillation, and chromatography. This is a term that basically describes how you can put certain materials that are liquids, excuse me, at the bottom of like some filter paper, and the material will like crawl up the filter paper through capillary action and that little attraction there, and it'll actually separate things that way. So that brings us to another term, which is called an emulsion. And an emulsion is something that kind of is something you're really familiar with, really, even though you probably aren't familiar with the word. And this is the idea that you can take immiscible liquids and somehow get them so that they're spread throughout one another, and then they stay in that form. Okay, so an example would be mayonnaise. What? Yeah, mayonnaise. And then you've got homogenized milk. So we'll talk about those a little bit. Here in this case, you can see we have this oil and water separation, and there's acetic acid in between. Okay, so that's the vinegar, right? Acetic acid is another name for vinegar. And so these guys are staying separated. But what happens if I put a chemical in here, okay, and this chemical has a nonpolar component, and it has a polar component. Well, the polar component is going to be attracted to all the water molecules. The nonpolar component is going to be attracted to the oil molecules. And so when you do this, you can actually get them to stay together. And so if you've ever gotten some Italian salad dressing from the store, it might not separate out like the one you make homemade. It might stay together. Why does it stay together? Because they put a chemical inside that acts as an emulsifier. And so it then has both positive and negative parts to it. And it actually is holding all that stuff in solution. Okay, it keeps it as one single phase. And so this is called an emulsion, where you have the liquids spread throughout one another and normally would be immiscible. Good example here, you can see cream from the far away naked eye view. It looks like it's just a single pure substance. But if you magnify it, you see all these little drops of fat or lipids. And all these little drops in here, that's all part of the fat that is in your cream. And that might sound like a horrible thing, but it's not, because we love the taste of fat in all sorts of food. So what do we do if I'm a farmer and I've milked my cow and I put it in the refrigerator? If you've ever done this, you've seen somebody do this, the milk will separate into the different layers. You've heard the phrase, the cream rises to the top. Well, if you just leave that milk there, the fatty stuff comes up to the top and the watery stuff stays at the bottom. The cream rises to the top. And of course, we love cream, right? Strawberries and cream, cookies and cream, right? We love cream. So how do we keep the milk that we buy from the store, how do we keep it from separating out like it does on the farm? Well, what we do is we go through a process called homogenization. And if you've ever paid attention to the label on your milk, you probably notice it says homogenized somewhere on there. What does that mean? Well, in this particular case, we're taking the liquid that is the milk that has these fat droplets in it, and we put it through this tiny, tiny little opening, which makes a really, really, really tiny fat droplet. Those really tiny fat droplets are small enough that water can then surround them and hold them up in solution. And so they're just showing you one way that they use to homogenize milk. There are other ways as well, okay? But this is not the same thing as sterilizing the milk. There's sometimes, the process called pasteurization, which is heating and cooling over time, and that helps to kill the bacteria in the milk so that the milk will stay good longer. That's different than homogenization, okay? Homogenization, just make sure it doesn't separate into the two different layers of fat and watery stuff. And then pasteurization is actually going through and killing the germs. But they do, I don't know, people do kind of confuse them together sometimes. All right, so what about gasoline? If we take crude oil, we turn it into gasoline. How does that happen? Well, I just want you to take a second to look at this because it's really a cool diagram. If you look here, we can see that our crude oil, that's the stuff that comes from the barrels out of the ground, right? It comes from out of the ground, we put it in barrels. We start with that crude oil here and it heats it up. And as it heats it up, the different molecules are going to separate out. The really light ones are going to go way up here to the top, okay? Liquefied petroleum gas, methane basically. That's going to be like your CH4, right? It's going to be really, really small particles. That goes all the way to the top. And you also have these other smaller particles. Gasoline has like 8 carbons, right? So that's a kind of smaller carbon particle. Kerosene, diesel oil, lubricating oil, fuel oil. These would have many, 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 many carbons in them, right? And so those many carbons are weighing it down and they're heavier. And so even though you heat it, it doesn't rise up as high. And so what happens is you collect all of these different types of substances based upon the number of carbons they have, and then you get all of these different chemicals that we use for fuel and various different things from the crude oil that comes from the ground, okay? All right, so let's see if we can meet our objectives that we set out to meet. Can we compare and contrast the properties of suspensions, colloids, and solutions? Yes, and we can tell you about other things too, like emulsion, and we can talk about the craziness of the Tyndall effect and how light goes through it in certain situations, etc. Can we identify ways to separate the different kinds of mixtures? Yeah, so we now know about like filtration, we know about distillation, decantation, we know about these different types of ways to separate parts of our solution, okay, including chromatography, right, that we can separate them that way. All right, well, it's a late night for me, so I'm going to sign off, and I hope you guys have an awesome time. I hope you had an awesome time learning about this, and I will see you on the flip side. God bless you. Have a great day.